Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. This lecture is a part of the lecture series on DC machines. And in this lecture, I will discuss the basics of DC generators. So, generators convert mechanical energy to electrical energy. In DC generators, the phenomena which is taking place is dynamically induced EMF, which is also called motional EMF. So the basic phenomena in DC generators for inducing the EMF is Faraday's law of electromagnetic induction. So for Faraday's law of electromagnetic induction, there must be a time varying flux. In transformers, that time varying flux is produced due to the sinusoidal supply connected at the primary winding. But in DC generators, the flux is constant, but the coil has to be moved continuously or the coil has to be rotated continuously in either clockwise or anti-clockwise direction. So when the coil is moving in the constant magnetic field, the flux linking with the coil will be changing at every instant, and due to that changing magnetic flux, EMF will be induced at the terminals of the coil. So when a conductor moves in a magnetic field, EMF is induced across its terminals, and it follows Faraday's law of electromagnetic induction. It has two parts or two requirements. First of all, we need the magnetic field, right? So magnetic field is an essential component of a DC generator, and we must have a conductor which is continuously moving or rotating in the presence of magnetic field. So these two components are essential, and after having these two aspects in the DC machine, we will be having induced EMF at the terminals of the DC generator. So let's discuss simple loop generator. And a simple loop generator is basically a single turn coil or a single loop coil which is placed in the magnetic field. This is the constant magnetic field, and it has one north pole and one south pole. And the magnetic flux lines are originating from the north pole and they are terminating at the south pole. So these dashed lines are actually pointing out the direction of the magnetic flux, and it has two sides. One side is AB, the other side is CD. So these two sides are actually cutting the magnetic flux. So they will be contributing to the EMF, and these two sides BC and AD, they are actually parallel with the flow of the magnetic flux, so they will not be contributing any Faraday's law, right? So there is no cutting of the magnetic flux through these two sides. So there will be no EMF induced in these two sides of the coil. So there are two slip rings in this system, and the two ends of this coil are connected to the two slip rings. This is the first slip ring F, and with this slip ring we have a carbon brush. Similarly, this is the other end of the coil. This is also connected to this slip ring E, and this slip ring is actually connected to this carbon brush. Now these slip rings are actually moving along with the coil. As long as the coil moves, these slip rings also move, and these carbon brushes are stationary. So they are continuously sliding. The slip rings are rotating with the coil, and carbon brushes are stationary, but they are continuously touching the slip rings, right? To carry the current which is induced in these coils. So that current actually um, come to the slip rings, and then that current enters these carbon brushes, and these carbon brushes actually provide the current to the external circuit. So this is our external circuit or the load where we want to use this electricity. So let's suppose this side AB is currently at the left hand side, this side CD is currently at the right hand side, and this coil is rotating in the clockwise direction. And we have to apply Fleming's right hand rule. In DC generators, we apply Fleming's right hand rule. In DC motors, we apply Fleming's left hand rule. So the right hand rule in DC machines is applied by pointing the index finger in the direction of the magnetic field. Thumb should be in the direction of motion of the coil or motion of the conductor. Then the middle finger will correspond to the direction of the current, right? So this is the right hand, and with this convention, we can evaluate the direction of the induced EMF. So the direction of induced EMF will be actually the direction of the flow of current. So by applying right hand rule at this side, the direction of current will be upward, and at this side the direction of current will be downward. So it means the current is going from A to B and it is coming from C to D, and that current will enter the slip ring E, and from the slip ring E that current will enter the slip ring F through this path. So the direction of current is from right side to the left side. So that direction of current will cause positive induced EMF across this load resistor. Now let's consider that the coil has rotated by 180 degrees. So this side of the coil AB has actually moved to the right hand side, and this coil CD has moved to the left hand side in front of the north pole, and this side AB has come in front of the south pole. So again, by applying the Fleming's right hand rule, the direction of current will be upward in front of the north pole and it will be downward in front of the south pole. Now this side AB has actually a current which is flowing in the downward direction, and this side is connected to the slip ring F. So the current will be entering this slip ring F, and through this carbon brush, that current will be entering this load resistor from the left hand side, and from the right hand side it will come to this carbon brush, and from this carbon brush it will pass this slip ring and then come to this side DC, right? So we can see that the direction of current in this case has reversed and it is flowing from the left to the right direction of the load resistance. So the induced EMF as a result of this direction of current will be negative. So we will have a negative half peak or a negative half cycle of the induced EMF. And overall, the induced EMF which is available at this load resistor is sinusoidal in nature. So this is the output of this generator when we are using these two slip rings E and F, right? So E and F are the slip rings. Now the thing is we have to achieve DC voltage. So we have to replace these two slip rings with the split rings or commutator. So I will tell you what a commutator is, but before that, let's read this. When the plane of coil is parallel to the magnetic flux lines, flux linkage will be minimum, but range of change of flux will be maximum. So induced EMF will be maximum. Similarly, when the plane of the coil is at right angle to the direction of the magnetic field, the flux linkage will be maximum, but rate of change of flux will be minimum. So we all know that whenever we have a maxima, the rate of change of that quantity will be zero. So in order to evaluate the maxima of any quantity, we have to take the derivative of that quantity and equate it to zero, because at the maximum, the rate of change is minimum, right? So at that point, the induced EMF will be zero or induced EMF will be minimum. But when the plane of the coil is parallel to the magnetic flux lines, then flux linkage will be minimum, but rate of change of flux will be maximum. So at that point, the induced EMF is maximum. So this is the Fleming's right hand rule, and this is the induced EMF. Now let's replace these slip rings with a commutator. So here we have a north pole and south pole again. In the same way, here we have the coil, but the two ends of the coil are now connected to a commutator, and this is called a commutator, which has two segments, and in between we have a mica insulation, and this is called a commutator or a split ring. And here we have two carbon brushes, and this is the insulation, which is mica insulation, and it prevents flow of current within the commutator segments. So in this case, the current is flowing upward in front of the north pole, and it is flowing downward in front of the south pole, and it will be entering the B segment of the commutator, and from this carbon brush it will be flowing in this direction, and from left to right in the load, and then it will enter this carbon brush, this commutator segment A, and then it will enter this side AB. So when this coil moves by 180 degrees, then let's see what happens. So after 180 degrees of coil rotation, This is the direction of current in the two sides of the coil. And now this segment A has also moved by 180 degrees. Here the commutator segments were A and B in the left and right direction respectively. Now the commutator segments have also moved and it is B and this is A. So now the current is entering this A segment and these carbon brushes are stationary and they will collect the current from this commutator segment which has also rotated, and the direction of current again is same uh, due to this commutator action, and the direction of current is again from right to the left, and again we will get a positive half cycle or a positive pulse at the output terminal of this DC generator. So in this way we can use commutator to achieve direct current, right, unidirectional EMF. So with this mechanism we will be establishing a DC generator, right? So now that was a simple loop generator, and we have discussed how a EMF can be induced unidirectionally in a DC generator. Now, practically, DC generator has two parts. First part is stator, the second part is rotor. And first part, stator has further three parts: yoke, pole cores, and pole shoes, and field winding. And rotor also has four further parts: armature core, armature winding, commutators, and carbon brushes. Now we will discuss them one by one in detail. So yoke, this is the outer frame of the DC machine. It serves two purposes. It provides mechanical support for poles and acts as protecting cover for the whole machine, and it carries magnetic flux produced by the field winding. So here you can see this is the yoke, right? So this outer frame is the yoke. It provides the protecting cover for the whole machine. The rotor is placed in this area, and here we have pole cores. These are pole shoes, and these are the field windings. The field windings produce magnetic flux, and that magnetic flux actually passes, or that magnetic flux actually flows through this yoke. Now the yoke can be made either by cast iron or cast steel. For small machines we can use cast iron, for large machines we can use cast steel, and cast iron actually has higher hysteresis loss and cast steel has low hysteresis loss. In small machines, the hysteresis loss is already small, so we don't bother uh, about using the cast steel in small machines. But in large machines, hysteresis loss can be very high, so we have to use cast steel to minimize the hysteresis loss. Next, we have pole cores and pole shoes, and it serves two purposes. The pole shoes spread out flux in the air gap and they support field coils. They are joined to the pole cores by screws. Pole cores and pole shoes are laminated to minimize eddy current losses. So these are the pole cores over which we have done the field winding, and these are the pole shoes. And pole shoes have a slightly bigger cross section as compared to the pole cores. So due to the presence of these pole shoes, these field windings cannot come out of these pole cores, and they also cause uniform magnetic flux through this air gap region. And in this air gap region, we will place the rotor. So field winding, we can use copper wires. They are former wound for the correct dimension, and a wound coil is put into place over the core. Coils are laminated. So laminated copper coils are used for the field winding, and they are first wound on a former, right? Then former is removed, and the coil itself is plugged over these pole cores, and after that these pole shoes are mounted with these pole cores by means of screws, which has been also discussed in this statement. Now we will discuss the parts of the rotor. So first part of the rotor is armature core. It houses armature conductors and causes them to rotate and hence cuts the magnetic field. It provides very low reluctance path to the flux from armature from north to the south pole, and it is cylindrical or drum shaped. It is built up of circular sheets, steel discs, right? So this is the cross section of the armature core, and you can see there are some teeth over the outer periphery, and this is the keyway. At this keyway, we will mount the shaft of the engine, which will provide the mechanical energy to the armature. Because in DC generators, we have to provide the mechanical energy, and the generator will produce the electrical energy. So that mechanical energy is provided by the shaft, which is mounted at this keyway, and these are the slots at which armature winding is done. And we have kept some air holes, and these air holes actually provide cooling to the machine. So it is built up of circular sheet steel discs. Holes provide axial flow of air through air ducts for cooling purposes. So this is armature core, and armature winding is done in these slots. They are also former wound in the form of flat rectangular coils and are then pulled in a proper shape in a coil puller. Laminated conductors are placed in the armature slots. So armature winding uh, will be discussed in the next lecture in detail. So I will explain how the armature winding can be done in a DC machine, and what are the types of armature windings and what are their characteristics. Next segment is the commutator. It facilitates collection of current from the armature conductors or armature coils. It rectifies alternating current to direct current in the external load circuit. It is a cylindrical structure and is built up of segments of high conductivity. These segments are insulated from each other by thin layers of mica. And in DC machines, number of commutator segments are equal to the number of armature coils. So last part is the carbon brushes. Carbon brushes are actually stationary in a DC machine, but they are part of the rotor, right? So carbon brushes are part of the rotor, but they are actually stationary. They are not rotating, and they provide the static circuit at which the load can be connected. And these three parts are actually rotating, but carbon brushes are part of the rotor, because in a DC machine, stator is separate and rotor part is separate. And the carbon brushes are actually part of the rotor. So that is all about our lecture on introduction of DC machines or DC generators. So that was the introductory lecture on DC generators, and we have discussed some basics of simple loop generators, slip rings, and split ring or commutator difference, and Fleming's right hand rule. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.